Determining the impact of chlorine ion chemistry on ozone loss in the middle atmosphere during very large solar proton events. By Monali Borthakur, Mariam Sinhuber, Alexander Lang, Thomas Redman, Peter Brasic, Gabriel Stiller, Thomas von Klarman, Bernd Funk, Ilya Yusoskin, Jan Mac Wissing and Olesya Yakovchuk. The present study determines the impact of chlorine ion chemistry on ozone loss in the middle atmosphere during very large solar proton events. This study involves solar particle events, SPEs, which can also induce geomagnetic disturbances in the Earth's magnetosphere leading to energetic electron precipitation, EEP events. Solar coronal mass ejections can accelerate charged particles, primarily protons, to extremely high energy, resulting in solar particle events, SPEs. Because of geomagnetic shielding, such energetic particles can precipitate into the Earth's atmosphere, particularly in polar regions. Ion chemistry can cause SP-induced chlorine activation, which depletes ozone in the polar middle atmosphere. To examine such events in the Northern Hemisphere, NH, we employ a cutting-edge 1D stacked box model known as exoplanetary terrestrial ion chemistry, EXOTIC, which includes atmospheric ion and neutral composition. Measurement data from the Michelson interferometer for passive atmospheric sounding, MIPAS, on Envisat were used to evaluate the model results using the Halloween SPE in late October 2003, a well-known large event, as a test field. Sensitivity tests were carried out for different model settings with a focus on the chlorine species of HOCl and ClONO2 as well as O3 and NOE. The model studies were carried out in the Northern Hemisphere for a high latitude of 67.5 degrees N, inside the polar cap. Ozone formation was observed after the event, which is also due to the impact of chlorine ion chemistry. For the Halloween event with temporal ionization rates, ozone loss of 2.4% during daytime and 10% during nighttime was observed during the event, that is due to chlorine ion chemistry. Ozone formation of 2 to 4% was also found after the event both during daytime and nighttime. Comparison of the simulated effects against MIPAS observations for the Halloween SPE revealed rather good temporal and spatial agreement for HOCl, ozone and NOE. For ClONO2, a good spatial agreement was found. The best model setting was the one with full ion chemistry where O1D was set to photochemical equilibrium. HOCl and ozone changes are very well reproduced by the model, especially for nighttime. HOCl was found to be the main active chlorine species under nighttime conditions, resulting in an increase of more than 0.2 ppbv. Further, ClONO2 enhancements of 0.2 to 0.3 ppbv have been observed both during daytime and nighttime. In a nutshell, the most appropriate model setting delivers satisfying result, i.e. the model can be considered to be positively validated. As seen from the model simulations, both events were able to perturb the polar stratosphere and mesosphere, with a high production of NOE and HOCs. Longer lasting and stronger stratospheric ozone loss was also seen for the extreme event. Qualitative difference between the two events and a long-lasting impact on HOCl and HCl for the extreme event was found. Chlorine ion chemistry contributed to a stratospheric ozone loss of 2.4% during daytime and 10% during nighttime during the Halloween SPE, as seen with time-dependent ionization rates applied to the model. Furthermore, while comparing the two events just for the event day, an ozone loss of 10% and 20% was found during the Halloween SPE and the extreme event respectively, which was due to the impact of chlorine ion chemistry. Thank you for watching this video. Please subscribe our channel for watch more scientific research videos.